Okay, first of all, we're trying to get at the what part, not the how. John has been trying to tell me that, and I'm telling him, we both tell each other this thing, but it's the what that we're after. And what is sort of a hard thing to do because some of our, well, a fellow I have a great admiration for is Dr. Richard Feynman, who always said we don't even know what energy is, or what force is, or for that matter, some of the basic things. We know how it does things, but we don't know what it is. So we are really after the what part, and I'll kind of build a framework. I'm going to try to see if I can build a framework around this. And uh, okay, I see things popping on my screen here. So hang on just a second. So anyway, this part of the work involves my software, and I've been working since '93, and I've had some interesting things happen over time. I had a stint at NASA at Jet Propulsion Lab. I was a principal investigator in '98 and 97, 98. It wasn't directly involving my project, but it was a test I wanted to do on the Cray J90, and I ran a test there to see if I was going to get some kind of interesting results. So anyway, ultimately, that was out of the way, and then I continued on with my work and see if I can. It was like a what do you call it, a litmus test for certain things I was after, and then I continued on, and then I found myself developing a software that would do these three things. Well, what I'm covering is called I call it the AUP, or the Autonomous Universal Predictor, which is in this box that you see. It's a section of the software application. Well, okay, so basically it's the part that involves me interfacing with the sensor data. Okay, it's there where where you need to be able to separate the noise from the signal. Okay, and what I'm doing is not like your standard filters that are used in many applications. What I'm doing is something that is quantum, and I'm going to get into that in a moment. Let me see if I can. So what I'm going to cover in the next few slides is going to be these three parts: the feature collector, the LabVIEW spectrum, which is an ancillary process, and then this cross correlation across the sensors. Okay, so I'm going to go to the next slide. Okay, so it says here that the quadrupole operates. This is a feature collector portion. The quadrupole operates like a magnetic resonance imaging, an MRI, on a wafer or a disc. So if you think about it, what we got here is an MRI, a magnetic resonance imaging in a sense. But what we're doing is, instead of putting a human body in there, we got a lump of material. Well, it's not a lump of material. It's a substrate where it could be something that's highly electropositive, and then you got something out on the as a conductor that's highly electronegative. Okay, and then in between you could have something that's like a gate. Okay, but the point behind here is that we're matching the frequency to the material, whereas most folks are trying to match the material to the frequency, and it's far more difficult to do it that way than the way we're approaching it. This allows us to work with all kinds of materials, and in a way, see if we can test out this hypothesis which is very well motivated, that there in fact could be a IU, or an information universe. Okay, and I'm going to try to show you how that connects with something that's already in a way being done, and we did an experiment at UCI in 2006. I'll explain that in a moment. So the sensors collect signals measuring changes in the material properties. We got here thermal, gravitational, electric, magnetic, from the IU signal source. Okay, so as John mentioned earlier, that we're looking for anything interesting. Okay, and normally, well, not normally, what you want to see is you want to be able to observe something. So that was why I mentioned earlier that the substrate should be having something that it wants, or something it wants to give, excuse me, and the conductor could be having something that it wants. So there has to be already some kind of a dipole in place. Some folks would call it, like Tom would call it, Tom was a close friend of mine, like John. In fact, John Searle, Tom, and I would actually have three-way, moment. I'd be the John, and we'd get on the phone and be talking with Tom. And this was a frequent. We were actually Dr. Clymer. We were all working on a effort to look at John's project in a different light. And anyway, it was an independent thing, and it's kind of resulted in this, that what we're doing. I won't get into that at the moment because it's easy to divert attention to that. What we found out is Tom would say, well, you got to have broken symmetry. He keeps saying. Well, what he's saying is that you better have some kind of a dipole so that you can see something, observe something. That's the goal here. And so we don't know what we want to make sure is we have to make sure that we have a way to regulate, disturb, regulate, and control. And that means this is something, this is a dynamic phenomena. Okay, this is highly nonlinear dynamic phenomena. So you are in a quantum soup. Okay, and in another thing, I'm focusing on that section on the collecting sensors collecting signals. What we're saying here is that these quantum particles are having a conversation. I'm trying to remember the physicist at Caltech who said this. It's excellent on YouTube if you could find it. They're having a little conversation. What you don't want to do is you don't want to zap them with noise. What you want to do is sneak up on them and eavesdrop and see what they're talking about. Anyway, that's the kind of idea here. And I'll get into that. So it says here, many sensors and signals can vary for each, which means we're talking about changes that can take place on the wafer, everywhere. We're talking about a wafer, but it could be a disk, okay? What that means is that we can have, you can imagine that the disk is representing the X-Y axis and that the sensors are on the Z-axis, okay? And they're not necessarily, it's a non-invasive approach, right? So they're not necessarily in contact with the disk. So they could be, a distance away, but not necessarily in direct contact. So this is a way to non-invasively get the signal despite any noise distortion. And by the way, noise in a situation like this, which is dynamic, is pretty much anywhere. You can't say that there's one optimum location for a sensor. These sensors could be picking up noise anywhere. And so we have to be able to separate that noise from the signal. Now, it says here, goes on here, signal features, entropies, are swiftly collected and compared, contrasted across the sensors. Okay, so what that is, and I'm going to try to see if I can see what that is this. Okay, what I'm doing is I'm taking I'm taking these signals that are coming in, and I'm getting a measure of their entropy. But what I'm doing that is different than what you'd be doing in the standard modeling usually involves linearization of things, okay? And it also requires that you have to it operates in a classical sense. I'm not operating classical. I'm operating quantum, which means that, and I know that, then it's going to be kind of difficult to understand this if you're not used to the quantum stuff. But imagine this, you got to be able to visualize. I like to make things simple. I want to make it so that everyone can understand what's going on here. Imagine flipping a penny. Okay, if you're flipping a penny, it's when the penny's flipping. That's when you want to know what's going on. You don't want to know what its state is when it's finally landed. I'm not interested in that. I'm interested in the state space of the flipping penny. Okay, so imagine zeros and ones flipping around, spinning up and down. Okay, you can call them the spins, you can call them what you want to call them, but they're flipping. Imagine these ones and zeros are flipping. They're superpositioning. Okay, they're overlapping each other. That's our quantum world. And what that means is that you want to know the entropy state space of that flipping itself. Okay, so I don't let those things land. I'm not in the world of classical. I'm in the world of quantum. Okay, so what I'm doing, when I say I'm getting the entropies and they're swiftly collected, I'm talking about entropies of the state space of these things flipping around. Okay, so then these are compared and contrasted across the sensors. Okay, next slide. So here I'm telling myself the next slide. I'm actually in control. Okay, so here we go. We got sweep one. So what happens is that I'm concerned about two things. I'm concerned about precision and I'm concerned about accuracy. Okay, so I have a system that is autonomously doing the data mining of the sweeps. Okay, excuse me, of the measurements. But what I'm doing is when I'm taking measurements, let's say this, so this represents the first 100 increments. Okay, how would I explain this in few words? Maybe I might not be able to do this in a simple way, but what it is that imagine that you have 100 qubits. Yeah, imagine 100 qubits. Okay, 100 qubits. So what I'm doing is I'm getting a measure of the amount of entropy treasured in the qubit individually as this is happening. Okay, and in there I'm going to find out that some of them are excuse me, some of them are tending to be negentropic or negative entropic. Okay, and then some of them are being entropic. So in this, the blue lines represent negative entropic. Red lines represents positive entropic. Okay, so that means entropy is towards disorder. Negative entropy is towards some kind of a dynamical structure. Okay, it's all dynamical. Okay, now this, you can look at the first 100 qubits as an aggregate. Okay, now one measure is not good enough for me. So what I do is I take multiple measures like that. Now this is just 3 attempts. I can take 1,000 of these attempts. Okay, and I'm just talking about the first 100. Okay, you can represent that in terms of some kind of a squiggly. We call it a squiggly, like some kind of a disturbance. Whether we are inputting it into the system, but I'm particularly interested in the system's feedback, because what we're inputting into the system, we already know what we're inputting. What we're interested in, what's the system's feedback. So I'm catching this. Now the precision has to do with how many times I'm sampling in generating these measures, but the accuracy has to do with how well my measures are. So imagine, so I got to give you an example, an analogy. I don't like to beat analogies to death, but you got to see an analogy here. So in a case like this, you got to think in terms of where you're signing your name. Okay, imagine your signature, the signing of your name is sort of like an aggregate. Okay. Now if you sign your name again, it's not going to be exactly the same signature you had before. It's going to be slightly different. Okay, and so what we're doing here is we're trying to show that there's some kind of stochastic behavior taking place in this 100 qubits. Okay. Now, just kind of bear with me if there's something that's not quite making sense. It's okay. We can discuss in the Q&A if time permits. So we go on. So what I did is I also said that if there is a researcher involved in something like this, they may want to see an ancillary step so they can visually see what's going on. Okay, it's easy on the eyes. So what I did is I talked to some folks at LabVIEW in 2005, 2006. I said, hey, gentlemen, can you help me out? Can you create a subroutine for me? Because I was working on I didn't get any kind of special grant. What I was doing is I was working with very little. So I tried to get, what I could. And then they did a little subroutine for me. And what I did is I generated my data. I piped it to an Excel spreadsheet. And then I sent that, through the LabVIEW subroutine. And what LabVIEW did, LabVIEW National Instruments, so it generated color hues. You can see here, dark fringes were the entropies. Well, dark fringes are the penumbras, which we call them umbras, and the penumbras are the illumination and shades. Okay, so you can see what that means is that it'd be really easy on the eyes if you were to see something in a timestamp. And going on to the next section, to the next bullet there, it's umbras correspond featured entropies, and penumbras correspond featured negative entropes, negentropies. Okay, what what that did is it led me to UCI. So I was scouting around. I didn't know where to go. I started saying, well, I need to find somebody who really has a need for something like this, because this is an unusual case. So I said, I got hold of a gentleman, UC Irvine. I can mention his name if you like, but it's right now. I just want to cut through all this and get to the key things. We sign a non-disclosure. There's certain things I can't disclose, but what I did is, what I'm going to share with you is what I did. So it was a fMRI imaging, and what they were doing was they were working with EEG, electroencephalogram, and what an EEG does. Let me just stay on this slide for a moment. EEG, what you got is you got a person, and on their head they have topically all these sensors on their head. It's non-invasive, and what they're trying to do is they're trying to collect the a person's tapping their fingers, for example, or they might be looking at something. They might be doing calculus. I don't know. They might be doing something cerebral. That's the idea here. And what you're doing essentially is you're sending an input into a neural system, okay? And this you can imagine to be the IU, the information universe, okay? And this comes back to Dirk's work that Dr. Clymer, John mentioned earlier. What is happening here was that a person could be tapping their finger, and so they have. He gave me 8 sensors, and he said, okay, of the 8 sensors, I want you to tell me whether any of these sensors are they able to cluster, kind of the way John is saying. You're saying the same thing. Can we find a correlation between these guys? Because then we were learning something, right? Anyway, what happened was I went ahead. I took his hexadecimal data. That's how it was given. It was given to me in terms of hexadecimal. And what I did is I took, for example, for sensor 3, I took the hexadecimal data and I converted to my measures. Now again, remember, these are measures of entropy in a quantum world, and I know this, and it's going to be a little bit tough to kind of, maybe for those who are not used to the quantum, it's going to be kind of difficult to explain that in a few words. But I'll try to see if I can, get across to you in the subsequent slides. So I don't know if you can see this. It's going to be hard for me to, and if I can, let me see if I can bring it out. So if you can see these numbers, you can notice that the numbers are not that different. They're not that far apart. In a sense, it's kind of like what John was saying earlier, that I'm not making radical moves. My moves are just like that, in increment up, increment down, somewhere in the middle. What I'm doing is I'm trying to get a way of honing in on some particular kind of particular kind of change, and see if that change is telling me anything about a degree of entropy or degree of negative entropy. Okay, these are entropy measurements, okay, between 0 and 1 that are treasured in each qubit, okay? So you can see this doesn't really change much, and it can get very precise depending on how, very accurate and precise. Now, precision has to do with how many times I'm running it, okay, as I showed you in the earlier plots, okay? Now, let me zoom back out of this. It may be, okay, so what I did next is this. If I can move to the next slide, hang on. What's going on? Bear with me. Let me see what's holding me up here. Escape there. I got it. Okay. So what I did is, if you see this right here, you see that arrow that you have there, that black arrow in the black box. Now, if you go to this slide, you see that on the bottom right here, you see that rectangular black box. It's the same thing. It's just been compressed. So you can see what that data sample right there really represents, just that little small slice down there. That tells you how much data I was generating from the information he gave me. Now, let me explain something here. He's giving it to me in static mode. I'm not interested in, ideally what you want something dynamic. This software is suited it serves its true purpose. It serves its true purpose in a dynamic situation. In other words, we don't want to be getting this thing after everything is done. We want to be doing it while it's happening. Okay, so that's what my software is actually suited for. In other words, it's designed for a dynamic phenomena. So when that person's tapping, I should be already getting all the stuff I want while it's happening. Okay, so I'm getting these measures. Ultimately, that's where I wanted what I can do. This was actually already datafied in raw data. Okay, and it was not cleaned. It was raw data, just the way it is. Okay, and they call it blind source signal separation. Okay, anyway, so these lighter hues that you see represent the penumbras, and any dark hues you see is representing the umbras. Okay, so the penumbras tells me that something interesting is going on, some kind of a dynamical structure, and the dark hues represent the entropies. It's the noise that's getting in. Now these strips don't it's not that you got a bunch of strips here. What you got is really one single strip. It starts from letter U. I labeled this, and if you can see the letters there, and it starts from letter U and it ends at letter W. Okay, now if that's hard to see, what I did is I created an inversion, and there's your inversion. So this is sensor 3 inverted. So you can see that it goes from V to W. So this is one long strip. Okay, I just happen to be looking at that one section of the strip just for your just to show you the connection between that and the measurements I was generating. Okay, so it really starts from V, ends at W. Okay, but imagine this thing going on dynamically ad infinitum. I'd be just there taking measures. Okay, and I'd be creating these umbras and penumbras for the experimenter. The machine doesn't need to know this. The machine can just directly input the measurements, and then from there we go. Okay, but I'm getting these things, and so what happened then is, so this is the this were all the slide sensors that I had 1 through 8, UCI, and these were our piped to Excel, and then I ran the NI lab subroutine for the researcher. So this was a sensor 1. And okay, and by the way, the top portion you see that you see the miscellaneous registered data, that was what we call registered junk data that's sitting there, and it's that this is because I didn't have a lot of things. I was not well equipped. I had what I had, shoestring budget, so I'm working with what I got. So I had to kind of I had to kind of do a lot of things manually. But really, what you want to do is you want a data that is not without any register. When you have a registry, if you're familiar with programming, in a register you're going to have a lot of junk ones and zeros if you're not completely using it. And I wanted to make sure I got rid of that. So that's why I'm also creating these inversions. So again, sensor 1, this is a piped version. This is the actual one that I showed to the researcher. And you have to, again, look at this as one long strip. Don't look at it as a bunch of strips. It's just one continuous strip. It starts at letter V at the top, and it ends at letter W on the bottom. And then here's sensor 2, okay, piped. And then here's this inversion. Here's sensor 3 again that I just showed you earlier, piped. And then this is the actual inversion, the way I wanted to present it to the researcher. Likewise, 4 piped. 4 was in this is happening very fast. I'm not sitting there and computing anything. I'm literally going in there and getting measures. Okay, and I'm not data dredging. I'm data mining, because when I do the aggregates that I mentioned earlier in that black plot, the plot with the black background, I'm getting a correlation, which I didn't get into detail. That correlation allows me to ensures me that my measures are mined, not dredged. Okay, so I can get into more details on that, but that's something I can get into later. Okay, so this way he's getting true measures. Again, sensor 5 piped, and then again here it is with the inversion. Sensor 6 piped, inversion. Sensor 7 pipe inversion. Sensor 8 pipe. This happened very fast, and I generated the results. And then what I did, I don't have this with me here. What I did is I actually cut these things in with a scissor, okay? Because I didn't have I didn't have all the ideal resources. What I did is, and then I actually stitched it together so that way it would be like one large panel of strips. So you can see sensor 1, 2, 3, 4, 5, 6, 7, 8, 9. And when I showed it to the researcher at UCI, he was able to look at this in timestamps and say, oh, it's interesting. I can see that sensor 8 correlates with sensor 6 at timestamp whatever. He would break it. He would take it into so many sections, and he said, well, that section right there correlates with what's happening here. And he would see that sensor 4 is correlating with maybe sensor 2 right here. So he'd see different correlations, saying, how when that person was tapping his finger, oh, something is happening in this part of the brain. Now, this is a very, very difficult problem to this day, right now, as I speak, in what's called multivariate neuroscience. It's a very, very complicated problem because they're dealing with what's the source problem. The source problem that they call is a problem that really affects all of science, everything in science. The source problem that they call in the neuroscience is basically this unknown origin of where this stuff is coming from in terms of signals that we don't know how to separate. I mean, you can't apply. First of all, you can't be thinking classical, but furthermore, they're not only in classical mode, they're thinking linear. So that really is that's even an additional handicap. So first of all, you got to stop thinking linear, and then you got to stop thinking classical, and you got to work in the quantum. And you don't have time to compute. You got to go in there and get the measures. And that's what I'm doing. It took me a while to do this. Okay, I mean, to come up with this stuff. Just like John's been working on his research, I've been working on mine since '93. Then this goes on here. So now I'm kind of speeding up here a bit. Let me see if I can. So cross correlation across sensors. Use timestamps, as I mentioned earlier. Visual ancillary spectrum, segmentation, AUP, OpEMCSS in tandem. So while I'm doing this, the ancillary stuff is for my visual, but OpEMCSS can just strictly start taking this stuff in and then start classifying. No limits on sensor quantity while sensors position and target wafer or disk location. So naturally, we want these things in areas where we're not going to get, we want to focus on areas where we really are interested in. And of course, I can get into the physics of this, but I don't want to get into it at the moment. I want to kind of stick to the experimental stuff and kind of tie it back to what John is saying earlier about, the need to make sure that things are clustering, okay? Otherwise, if we don't cluster, we can't learn. What I'm demonstrating here right now is I can cluster and I can find things that are correlating. This is a big problem. And anyway, now let's see. No limits on sensor quantity. Well, yeah, in general, because when you're in the world of quantum, right? When you're working with things in the quantum, you are pretty much, you're going to cut through a lot of stuff, okay, that normally you couldn't if you're in a classical world. Okay, so UCI fMRI researcher noticed immediate cross correlation by a visual cue, as I mentioned earlier. He saw right away, oh, that's something we didn't catch. It's there, okay. Sensors need to be in contact with wafer or disks, need not be, okay, but topical and non-invasive to materials. AUP bridges quantum to classical. It could be microchip. Yes, my software can be put into a chip format. Okay, so this is an interesting. Now, what is different from what I'm doing versus what's going on in the quantum world right now, including the folks at Google and again, I respect everyone's work and what they do, so I'm not telling anyone anything. All I'm saying here is I'm just saying that I'm doing something different than what the other folks are doing, in the sense that I'm not particularly interested in computation of any kind. I'm not particularly concerned with a special gate. I'm not trying to hack anything. What I'm trying to do is I'm trying to understand the quantum world and the information that's treasured there, okay? And there are certain things they'll tell you that you'll never get the complete information of the treasured that's treasured in a quantum bit. You'll get something partial. And that's true. I can relate to that because we are trying to, as I said earlier, we're trying to sneak up on these guys and try to eavesdrop on their conversation. And what that's an analogy to saying is that we're trying to find out exactly what is their state space. What exactly is, you can't quite zero in on it because noise is always going to try to distort it. But the way to keep noise at a bay, if you will, and this is sort of in the wave theory of information, where they're saying that the limits have not been reached yet because we're only scratching the surface. We need to come up with better ways to engineer and do system science to get there. Ultimately, what that means is that you want to have a way of knowing at least something about the state space of that quantum, the amount of information that's treasured in a quantum bit. But it could be partial, which is fine. But you want to do it in a way so it's direct. You're not computing anything. You're directly getting in there and finding out what's going on, because we don't have time. If this system goes into meltdown, we don't have time for that kind of stuff. We got to jump in and do something right away. I think there is a latency for the system to to do anything. So in a way that affords us time to do certain additional things that we need to do to improve our control system, so that we can get more rewards and we can continue to reward the system more rather than punish it. So that's important. Let's see, next slide here, and I'm kind of getting close to the end, so I don't want to take too much time here. So I said, okay, we can also use, since John's software was used at a graduate level for a master's program and higher, I presume, and I've used mine in a research at an advanced research level. It can be used to pursue R&D, and I by the way, just so you know about my background, yeah, I have a bachelor's in electronics technology, but I specialize a great deal in independent study and information theory for a long time, and then I pursuing a degree and finishing up a degree in mathematics, an accelerated degree, and then I'm planning to go for a graduate program. But I didn't want to do that until I had something that I could actually create a framework around that interested me, that can also I think help bridge a gap between the mainstream science and what we're talking about here, which is what I would call extreme science. That there's nothing wrong with it. It's just that it needs some kind of a framework, a knowledge framework for the folks in the mainstream to kind of wrap their head around. And I could talk about Caltech another time, but that's another discussion. But John and I had an interesting, very positive feedback. Now the next thing is, at first, if I was to do a distance, I did the hard part already. My main concern here is I need to do the formal work. But in effect, from what I've done from '93 to present with a stint at NASA and then some other work I've been doing, first my dissertation's already kind of in place. My first part would include what I just talked about. Okay, and then the second part would be covering my research collaboration with JPL. A little stint there with some tests I did, and then what I did with UCI, which I covered today at APEC. And the third part would cover some other work I've done. I was involved with LENR, low energy nuclear reactions at Cal Poly, with Dr. Robert T. Bush and I think it was Bob Eagleton. And that is an interesting research involving the work of Pons and Fleischmann that took place a few years prior. And there was a frenzy. Anyway, that's what I want to say, is that there, and of course I had also interaction with some other folks, including John and Tom. And then what we're doing now is kind of what it's led to. And we can discuss more of that. The business model, dollars and cents, I put that in quotes, cents. Intellectual property, defensive publishing, trade secrets, circumventing, not infringe, patents involving claims, specifically admixtures with synergistic effects of materials matching frequency. Okay, so I felt that it's important that I also have a business model. So for those of us who are engaged in this type of effort, that we have some direction. And it actually led me to write a letter. By the way, I'm very neutral when it comes to who's our president. I don't, whoever is our president, I always respect whoever's in office. So I've corresponded with President Obama, And I've also I had to correspond with President Obama on Star Trek initiative, and I also interacted with President Trump on another topic that's also on the extreme ends of things. It's just involving science. Okay, and that's not directly related to this. That's why I'm not going to get into it at this moment. It does have tie-ins, but not directly to what we're talking about right now. Anyway, but why I brought it up is because defensive publishing trade secrets process is hard to figure out. File for patent, but nice. We're dealing with a technology that does seem to have the best of both worlds, and I have to say it that way and frame it that way. It's the best of both worlds in making our humanity great again, and at the same time also help protect our country. Okay, because it does have naturally it's going to have defense applications. So we have to find a way to show that there is a best of both worlds. One way to do it is to have a way to keep the technology in a I'm trying to put this in a business framework that where the certain information is kept proprietary for obvious reasons, while you can still do research and development that can benefit the consumer, that can benefit all of us. Okay, we the people. Okay, but it can also have that other added benefit to make sure that we are also for national security reasons. When you say that, sometimes people get the wrong idea, but often you have to find this balance when it comes to certain kinds of technologies. And there I have John Searle, myself, Tom Bearden. I'm sure I know that the three of us we felt that way. There is this sort of a balancing effect. Go ahead. So this what it does is it affords us to continue R&D at high to mid low TRL tech readiness level. They use the TRL acronym at NASA. Low TRL is akin to NIDS, National Institute for Discovery Science. Yes, let you know that in the 90s, late 90s, right after it was a hiatus. So what based on the work of NIDS, I had a chance to speak to Kelleher, who's involved with NIDS, and some of the work that was interesting. I'll keep it in that ballpark, involving Robert Bigelow, and let's see what else. I was also in touch with Peter Sturrock at Stanford, and actually, and the reason I'm bringing that up is because I sent Peter Sturrock, Dr. Sturrock, a message saying that at the Pocantico conference that you folks had in '97, this was 2000 when I sent him the email. Said, was there any discussion, and then this is in quotes, was there any discussion involving the use of intelligent sensors for detecting any physical patterns in real time? And I was referring to that interesting work that was done by Robert Bigelow and NIDS investigation, on the ranch, that ranch episode. Okay, it's a difficult topic, and I don't want to get into it too much. That's why we call it low TRL. Okay, so it kind of allows you to continue to do research in that area while you still have spin-off technology. So there could be stuff that we can do now that could have immediate rewards and still do mid to low TRL. Okay, we're aware of the admixture material science, patents claiming synergistic effects involving materials matching frequency. Well, there are many of them, right? I think there are quite a few out there that are saying that, look, if we get this kind of material lined up with this, provided they can get 1 + 1 = 5, then they're getting something more than what they expected. Then they got a patent of some kind. We're not in any way infringing that. What we are doing is, what our goal here is to build a toolbox. And the toolbox would allow us to test different kinds of materials. And the way I described earlier, having certain something that you can observe, like a dipole effect, for example. But what we're doing is we're matching the frequency to any material. Okay, that way we're not infringing any of these folks. So this is sort of an interesting business model in the event if someone wanted to pursue this, this is a model that I'm kind of building around so that it can actually establish small business innovation research for continued efforts in this kind of extreme science. And with getting the help of our, getting the backing from our federal agencies and our, because the main thing here is that we want to make sure that technology like this is in the right hands, and it's also something that can help benefit, make humanity be a better place, because we certainly could use a technology that can get us, advance us further. Okay. And of course, I left it at this with Richard Feynman at the end. Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And I think Sean Carroll is trying to do the same at Caltech. So this is the summary of the presentation. If John wants to jump in. John, you there? No. Okay. Well, I'll just say it. So the summary of the presentation, the takeaway, is to understand the intelligent adaptive agent concept applied to control IU, disturbance regulation, understand operation of information universe regulation in the material universe, understand why quadrupole experiment is critical to safe research in IU regulation. So IU is, again, that information universe. Did I rush through a little bit too fast? Yes? No?
No, well,
you did good.
Huh?
I guess we got a little time for questions and answers.
yeah. Let me do this, guys. Let me do this. Let me mute you both out really fast. And then, sorry about that. So what I want to do is I'm going to put it on speaker mode, and everybody, please, you know what, here, I'm going to stop screen sharing. Oops. Yeah. Stop sharing. There we go. Sorry about that. I'm going to put it on screen share mode. Everybody, could you put your hands together and give Amar and John both an enormous hand? Gentlemen, thank you very, very much. That was a ton to work through. And it was very different than a lot of the stuff that we've covered here.